Laplace transformation is transforming a function from time domain to Laplace domain. When we say Laplace domain, it's the variable is s instead of, let's say, in time domain t. So if we have a function f of t, we want to transfer it into, we want to do Laplace transformation. So we want to transfer into Laplace domain. So that will be like this, f of t, and this is written as f of s, uppercase f and of s. So variable instead of t becoming s in Laplace domain. So it is defined as such. Fs will be integrating this from 0 to t. Let's say the function is defined from t is equal to 0 to greater than 0. So we integrate from 0 to infinity, and ft multiplied by e to the power minus st dt. So once we do this integration, it will be converted into Laplace domain. So what is happening in this integration? There is s here. If we look here, there is s here as negative s, and the integration variable is t, and we have limits there. So once the integration is done, because of the limits, t will disappear and s will remain. So we will get something in terms of s. That will happen, we can see that. So let's do one Laplace transformation. Let's say we want to do an exponential function. So ft is equal to e to the power minus at. We have that, we want to transform it. Let's say e to the power plus at. We could do minus, but let's do e to the power at basically. So this is our function. We want to find f of s. So 0 to infinity, so this is just e to the power t. So 0 to infinity e to the power at times e to the power minus st dt. This one we can write 0 to infinity e to the power minus here, and then s minus a t dt. So now once we do the integration, it becomes minus that. So it is, since the coefficient is negative, it becomes 1 over the whole thing, the coefficient. And this is the same thing, minus s minus at. After the integration, exponential function remains the same. So like that. Now this is 1 over s minus a. Let's write a bracket here. Once we plug in the limits here, this is infinity, so this will become, of course, e to the power s minus at, and I will write this again, infinity and 0. So when t is infinity, this term is becoming 0, and when t is 0, this is becoming negative 1. There's a negative here, there's a negative here. So this is becoming 1 over s minus a. Now we don't have any term, any t term, it is just s, and a is the coefficient of the coefficient of t of the exponential function. So this is the Laplace transformation. If we have, this is just one example, f of t is e to the power at. So f of s is 1 over s minus a. So this is how we can transform a function into Laplace domain, a time domain function into Laplace domain. And usually what we do, we don't do integration for each of the terms. There's a standard table which we try to memorize, and when we apply Laplace transform, when we apply Laplace transform, we just write it from the table. So one of the application of Laplace transform is when we deal with differential equation, it becomes like an algebraic equation. A time domain differential equation, when converted into Laplace domain, becomes like an algebraic equation, so the solution becomes easy. The other thing I would say, other benefit of Laplace transform is there's an operation called convolution, and this is of two functions. So in order to do convolution of two time domain function, an integration needs to be done. But if we can avoid the integration by converting to Laplace transform, which we will see later. So anyway, this is just an introduction. I probably will do one Laplace transformation of few more functions. Let's see.